Now, we shall study module 3 of chapter 7. In this module, we shall learn about 3 things. The first one is how to find the area under the coordinate curves. That means, we are going to find the area under the parametric curves, that is u1 curves and u2 curves. Secondly, we shall study about the geodesic coordinate, and the third one we shall study about the field of geodesics. So, let us start the first section of the third module of chapter 7, that is the area under the parametric curves. Now, in section 1 of module 3 of chapter 7, we shall learn how to find the area under coordinate curves, that means the parametric curves on a surface. The parametric curves, which are also known as U curves and V curves, will bound a region on a surface, and we are going to find the area under the bounded region between the parametric curves. Now, this area from the given figure, we can see that there are U curves, parallel U curves and parallel V curves, and if UV is a point on the coordinate system, then its neighboring points are u plus del u v, u comma v plus del v, and the other point is u plus del u and v plus del v. So, there are 4 points on a parallelogram, which is the bounded region by the U curves and V curves, which are coming like a parallelogram, and this area can be evaluated by the double integration given by the expression double integration root a du dv, where a is the determinant of A alpha beta. That means, the coefficient of first fundamental form. This is the expression where A is the determinant of A alpha beta, and we know from the first fundamental form how to find the values of A alpha beta. So, we can easily find the value of A, and if we put the value of A in the above expression, and if we integrate once by du and then by dv with the given limits, we can find the area for the bounded region. Now, let us see the example. Suppose x1 is given by 4 a square u by 4 a square plus u square plus v square, x2 is given by 4 a square v by 4 a square plus u square plus v square, and x3 is a into 4a square minus u square minus v square by 4a square plus u square plus v square. Now, we have to remember that this a is not the previous a, because that a is the determinant of a alpha beta and here a is a constant, and if we calculate the values of root a and if we put the values in the formula, we get this expression, that 16a square double integration du dv by 4a square plus u square plus v square to the power whole square. So, by integrating this we can find the area on the surface given by the above equation. Now, here we see that x 1 square plus x 2 square plus x 3 square is satisfying the equation of the sphere, that is x 1 square plus x 2 square plus x 3 square equals to a square, except the point 0 0 minus a. In vector form, we can express the equation in this form: r equals to 4a square u by 4a square plus u square plus v square, 4a square v by 4a square plus u square plus v square, and a 4a square minus u square minus v square by 4a square plus u square plus v square. So, we are writing the equation in vector form. So, R1 or we can write this one as RU also, that means we are taking the partial derivatives of x1, x2, x3 with respect to u, and we are getting this expression 4a square by 4a square plus u square plus v square whole square is coming out, and the other components are 4a square minus u square plus v square minus 2uv and minus 4au. So, this is the expression for R1, or we can say as RU. Similarly, we can find the value of R2, or we can say RV, that means we are taking the x1, x2 and x3, the partial derivative with respect to v. So, R2 is coming out this expression 4a square by 4a square plus u square plus v square whole square, and the components are minus 2uv, 4a square plus u square minus v square and minus 4av. Now, A11, that is R1 dot R1, that is in vector form, we know that A11 is actually R1 dot R1, and the expression is coming in the given in the right hand side, 16a to the power 4 by 4a square plus u square plus v square to the power whole to the power 4, and with the given expression in the right hand side 4a square minus u square plus v square whole square plus 4 u square v square plus 16 a square u square. Similarly, we can find R2 dot R2, that is A22, which is coming in the right hand side expression. And we have also seen that R1 dot R2, that is equal to A12 is equal to 0. That means, the coordinate system is orthogonal. That means the angle between the parametric curves is pi by 2. Now, putting the value of A in the formula, the double integration root A du dv, and after simplification we have this expression 16a square double integration du dv 4a square plus u square plus v square whole square. So, if the limits are given now, we can find the value of this integral, or in some other way, if we can find the value of this integral, we can find the area under the parametric curves on the given sphere. Now, let us see another example, another concrete example, where we have obtained the value of the area. Now, we see another example, that is x 1 is given by u cos v, x 2 is given by u sin v, and x 3 equals to a v. That means, for a surface of helicoid, and we are trying to find the area of the surface for the parametric curves bounded by, now we are giving the limits u equal to 0 to u equals to a and v equals to 0 to v equals to pi, and we have obtained that the area is coming this one pi a square root 2 by 2 plus a square by 2 log 1 plus root 2 square units. So, see how we are calculating this one. Now, we have expressed the equation in vector form equals to u cos v, u sin v and a v. So, R 1, that is R u, actually we obtain this value cos v, sin v 0. Similarly, R 2, that is R v, that means we are taking the partial derivative of R with respect to v, and we are getting R 2 equals to minus u sin v, u cos v and a. Now, R 1 dot R 1 is giving equals to 1, that is a 1 1 equals to 1. R 2 dot R 2 is equals to u square plus a square, that is a 2 2 is u square plus a square, and a 1 2 is equal to 0. That means, the coordinate curves or parametric curves are orthogonal for this surface. And previously we have seen that the surface of helicoid has the parametric curves orthogonal. So, now the area will be this one 0 to a and 0 to pi root a du dv, and it will give pi a square root 2 by 2 plus a square by 2 log 1 plus root 2 square units. So, we have seen that how we can find the area under the coordinate curves on a surface. Now, in section 2 and 3 of module 3 of chapter 7, we shall learn about two very important concepts, that is geodesic coordinates and field of geodesics. Now, geodesic coordinate system does not exist always for a Riemannian space, but if at some point the Christoffel symbols will vanish, then that system will be called geodesic coordinate system. And the second one, that is the field of geodesics, that is a portion of a surface where we can get some parallel geodesics, and in that portion is called the field of geodesics. So, now let us see a very important two concepts, that is the geodesic coordinate system and the field of geodesics. In section 2 and section 3 of this module, we shall learn about two things. One is geodesic coordinate system, another one is the field of geodesics. Now, we know that for a Riemannian space, the Christoffel symbols do not vanish at all points. Now, if there exists a coordinate system where the Christoffel symbols vanish at a given point, then that coordinate system is known as a geodesic coordinate system. Now, Christoffel symbols for the surface also we can find, and if at some point on the surface, if the Christoffel symbols vanish at some point, then we can say that the geodesic coordinate system exists on that surface. The point at which geodesic coordinate system exists is called pole of the given system. Now, this system is very useful for mathematical physics and in gravitational theory, where the pole is considered as the base point of some system, where the Christoffel symbols vanish, and this one is considered as the initial point for the system. Next, we consider the field of geodesics. Now, a one parameter family of geodesics on a surface is said to be a field of geodesics in a portion S1 of S if through every point of S1 there passes just once exactly one of those geodesics. That means, if we consider a surface and we know that there are geodesics on that surface, if the geodesics exist on that surface and if it lies on a portion of that surface S1, and if there are family of that geodesics which passes exactly one point within that S1, then that S1 is called the field of geodesics. Let us see two examples. The generating straight lines of a cylinder are the field of geodesics, because the straight lines, the generating straight lines are the geodesics and they form the field of geodesics on the surface of a cylinder. And for a plane, the family of parallel straight lines, we know that the straight line is a geodesic on a plane. So, family of parallel straight lines on a plane will form a field of geodesics. So, with these examples we can visualize about the field of geodesics. So, in module 3 of chapter 7 we have learned 3 things. First one is how to find the area under the parametric curves. We have seen that if a bounded region is done by the parametric curves, that means u curves and v curves, then we can find easily the area between that parametric curves. Actually, it forms like a parallelogram with the coordinate curves, and we have seen that area can be easily obtained by the double integration root a du dv by this formula. We have seen 2 examples that how to calculate this area. Next, we have learned about 2 basic concepts, though they are new, that geodesic coordinates and the field of geodesics. We have seen that generally the Christoffel symbols do not vanish at all points on a surface, but if at some point the Christoffel symbols vanish, then that coordinate system is called geodesic coordinate system, and at the point where the Christoffel symbols will vanish, that point is known as a pole. And the third one, we have seen the field of geodesics, which is a portion of a surface where the parallel geodesics will be there, and it form a region of the surface where a family of geodesics will lie. So, with these 3 very important concepts, we shall complete the module 3 of chapter 7.